As humanity cast an ever wider net across the cosmos, capturing evidence of thousands of worlds, an ancient question haunts us. Is anybody out there? The good news: we know vastly more than any previous generation. Our galaxy is crowded with exoplanets, planets around other stars. A healthy percentage of them are small, rocky worlds of a similar size and likely similar composition to our home planet. I invite you to embark on a journey through unexplored space in search of life. Our journey will begin with the search for planets similar to our own. Then we'll investigate whether life is possible nearby, somewhere in the solar system. And at the end, we'll find the answer to the question, why don't we see signs of alien civilizations? Latest research into solar activity shows that humanity's time on Earth is slowly coming to an end. The behavior of our star has resulted in big changes on Earth several times before, but what if future changes are so significant that our civilization cannot adapt to them? If we had to leave Earth right now, what are our chances of finding a new home? What new planets have been discovered by the scientists, and is there a new Earth among them? Let's find out right now. For starters, let's talk about what it is that we're actually looking for. All of the planets found outside of our solar system are called exoplanets, but not every exoplanet is suitable. For example, there are quite so-called rogue planets. They revolve around the center of the galaxy, not tied to any star. Due to the lack of conditions that only a nearby star could provide, these kinds of planets are not suited for humans. The main problems encountered in the search of exoplanets are the distance, their size in relation to their star system, and light. Unfortunately, unlike stars, very few exoplanets have enough luminance for us to see them in the light of a star that formed their system. Furthermore, the presence of such luminance can indicate certain problems. For example, a planet might be too close to its sun, and therefore too hot. When searching for a new home, we must also account for its location within its own star system. First and foremost, we want to know whether the planet is in the so-called habitable zone. The habitable zone refers to the distance from the star that allows for the existence of water in its liquid form. Additionally, the planet can't be too cold or too hot. A prime example of how hard it can be to spot the kind of planet we're looking for is the famous pale blue dot. A photo of Earth taken by the Voyager probe from the outskirts of the solar system really shows how difficult it is to spot something in space. Fortunately for us, there are several ways to find exoplanets. The most obvious way, direct observation, which involves observing the cosmos using telescopes and probes. But this method faces the issues of distance and luminance. As of right now, only a few planets were discovered via direct observation. For a planet to be discovered via this method, it has to be large and bright. Thanks to such characteristics, the planet 2M1207b, which has the mass equal to 10 Jupiters and surface temperature over 1600 kelvins, became the first exoplanet that could be observed using this method in 2005. The other method of finding exoplanets is the transit method. Most exoplanets were discovered using this method. The gist of this method is basically trying to notice the dimming of starlight over time. So why would their light dim? As the planet orbits around a star at a certain point, the planet would be positioned between us and the star, blocking some of its light. A good example of that are periodic solar eclipses we're able to observe from Earth. We know that when celestial objects are positioned in a certain way, we can observe the way the sun is fully or partially blocked by a passing planet or the moon. And so when we see a star being dimmer than before, We're observing the transit of its satellite, an exoplanet. The most studied planet found outside of the solar system using this method is Osiris. So hot and large that when it transits the star, it dims its light by 1.7%. It's so hot that it was nicknamed the evaporating planet. It was even found to contain water vapors in its atmosphere. The third most successful method of searching for exoplanets is the Doppler method. It used to be a primary way of finding exoplanets before the transit method. The method essentially uses a spectrometer to observe changes in a star's luminosity. When there is a relatively large object orbiting the star, its movement causes shifts in the star's light spectrum. One of the most fascinating planets discovered using this method is the Kepler 11c, which was found to have an Earth-like atmosphere containing helium and hydrogen. As of today, we know of around 5,200 exoplanets. However, only a small portion of them can be considered candidates for becoming Earth 2.0. There are good reasons for that. The first one is the classification of exoplanets. Let's take a closer look at the different types of exoplanets. We'll start with the largest and most diverse type, gas giants. So far, we've discovered over 1,500 of them, and they're all incredibly large. However, there is something that sets them apart from the gas giant found in our solar system, Jupiter. They are very hot. Normally, gas giants have a solid core surrounded by flowing gas like helium or hydrogen. And while on Jupiter the gases are cool, the gases on the aforementioned planets are so hot that some of them have a higher combustion temperature than that of our Sun. It goes without saying that these planets are not appropriate for habitation. Another type of exoplanets, just as prolific as gas giants, are Neptunian exoplanets. There are over 1,700 of them that we currently know of. These planets are more similar to Earth, both in their high content of metals and the presence of an atmosphere. Although they contain metals and their atmosphere contains hydrogen, helium, and sometimes even oxygen, these planets are usually either too far from the parent star, just like Neptune in our solar system, or too close, which results in them gradually burning out, something we are able to observe on our system's rocky Mars. Among the Neptunian exoplanets, there are two that present the most interest to us. Gliese 436b was discovered in 2007 and is unique due to the fact it is made almost entirely of water. On top of that, the planet's surrounded by hot ice with a temperature around 570 degrees Fahrenheit. It has an atmosphere that mainly consists of helium, and as the planet orbits its parent star, it leaves a huge trail of hydrogen. Gliese 3460b was discovered in 2012. Its atmosphere is also full of helium and hydrogen and is much more dense than Earth's atmosphere. It's possible that at some point of their existence, these planets will eventually have the kind of atmosphere conditions we need, but there's no guarantee that they'll be able to sustain those conditions. For example, Gliese 3470b loses around 50 to 100,000 tons of helium per second. But still, scientists seem to think that some of these warm Neptunian exoplanets are in transition and have the potential to form into an entirely new type of planet, a super-Earth. Super-Earth sounds promising, doesn't it? Well, don't rush to celebrate it. In this case, the prefix super doesn't mean it's better than Earth. It actually just refers to the size of the planet, which is several times larger than Earth, but smaller than the giant of the solar system, Neptune. Significantly fewer planets of this type have been discovered, around 900, but their composition is much more similar to Earth, and the conditions are closer to the kind we need for survival. A few super-Earths come to mind. The nearest super-Earth is Barnard Star B, located only 6 light-years away. However, it doesn't get much light from its parent star. According to the scientists' calculations, it only receives the equivalent of 22% of the energy that Earth gets from the Sun. The next interesting planet is Kepler 22b, an exoplanet 14 times bigger than the Earth, although it's theorized to be entirely covered by ocean, which means there's a chance that there could be life on Kepler 22b, since calculations indicate that the temperatures on this planet range between 12 and 70 degrees Fahrenheit. In July 2017, another super-Earth was discovered. It was named Lytton B. Its most interesting feature is that the amount of energy it gets from its parent star is very close to what we get from our sun, only 6% more. It's also likely that it's made of rock, and considering its atmosphere, the range of temperatures on this planet are very similar to Earth's.
Then very recently, at the start of October 2022, a new exoplanet that was assigned the moniker LP890-9c was discovered.
Not only is it in its star's habitable zone, the temperatures on the surface are pretty pleasant. At the moment, it's considered the second most prospective planet of this type for potential human relocation. And although super-Earths make scientists feel moderately optimistic, there's a rare but most prospective type of exoplanet, terrestrial or rocky planets. So far, only around 190 of them have been discovered. It's very likely that there are many more out there, but since their size is so close to Earth's, it's difficult to spot them, unlike gas giants or hot Neptunians. In the solar system, Earth, Mars, Mercury, and Venus are the four terrestrial planets. Outside of the solar system, planets ranging between half and twice the size of Earth are considered terrestrial, some of them being even smaller. Exoplanets that are larger than twice the size of Earth are considered super-Earths.
The closest and most similar in temperature and composition to Earth are Ross 128b and Gliese 667c. Ross 128b has quite a wide range of temperatures, between negative 76 and 70 degrees Fahrenheit, which is primarily due to its proximity to its parent star, whereas Gliese 667c has the average surface temperature of 80 degrees Fahrenheit, but it always faces the star with the same side. So it's possible that it already has primitive life forms around its pole, which is close to the star.
What method is humanity currently using to study space in search of exoplanets? The most effective tool at this moment among the ones out there in space is the Kepler Space Telescope. Even though its mission was supposed to only include 3.5 years of observing a relatively small part of the sky, it manages to observe over 100,000 star systems simultaneously. We're already familiar with the method of finding exoplanets used on the Kepler telescope. It is the search for the presence of planets using the transit method. Remember, the main principle of this method is observing periodic changes in the brightness of stars. Kepler's work resulted in finding over 3,400 exoplanet candidates, more than 1,000 of which were subsequently confirmed as planets by further research. In the end, it worked for over 9 years and ceased to function in 2018. The first 5 hot Jupiters were discovered thanks to the Kepler Space Telescope. A little while later, it detected the smallest known exoplanet, which is only 1.42 the size of Earth. Kepler 10b is the first one of the officially confirmed planets composed of iron. It's a shame that its temperature range exceeds 2,700 to 5,400 degrees Fahrenheit.
But the things considered most interesting among its findings are the Earth-like planets Kepler 438b and Kepler 442b, discovered in 2015, both of which are in the habitable zone of their parent stars and considered incredibly promising. Located in the habitable zone of its red dwarf, Kepler 438b still requires detailed study because the flares of its star, which are dozens of times more powerful than those on the Sun, they may cause considerable harm.
It's worth mentioning that even though the telescope stopped working in 2018, the data from its observations is still being received and processed. So it is possible that the list of candidates for Earth 2.0 would only expand. To replace the Kepler telescope, the TESS telescope was launched. in 2018. Unlike its predecessor, the TESS telescope will primarily explore the space nearby, limiting its search to a distance of 200 light-years. It is also worth noting that this telescope will observe the area more than 400 times larger than the area viewed by Kepler. While the Kepler telescope looked further into space in a more narrow sector, the TESS space telescope will first and foremost explore the nearest section of space. However, its gaze will cover a sector hundreds of times wider. Among the first successes of TESS is mapping of more than 75% of the visible night sky and identifying more than 2,000 exoplanet candidates based on transmitted data. Most recently, in August of 2022, TESS discovered the unique planet TOI 1452b, which is 67% larger than Earth, according to scientists. At the same time, 22% of its surface is covered by water. Calculations suggest that it receives as much energy as our Venus receives from the Sun, which makes it the ideal candidate for further study. It is expected that TESS will discover over 20,000 transit exoplanets, 500 to 1,000 of which will be terrestrial and super-Earth planets. As for the latest devices that will continue the search for exoplanets in the future, we have to mention the recently launched James Webb Telescope, which already had incredible results. You can find a video on our channel that will tell you in detail about every aspect of its work, as well as all of its features. Now let's briefly talk about why the JWST is necessary when we already have a substitute for the Kepler in the form of TESS. Both the Kepler telescope and the TESS telescope, although they were and continue to be incredibly powerful tools for observing space and stars, they still face the same problem as all photographic-type telescopes. Just like the Hubble telescope, the telescopes in question have certain limitations in their search, primarily to do with the spectrum of light they're able to see. In contrast, the James Webb Telescope has eyes that can operate outside of the visible spectrum. It has the ability to see farther and in more detail, the ability to look deeper and deeper into the universe and its mysteries through the gas clouds. And now we should give it credit for its achievements in the search for exoplanets. The first was a detailed study of the two exoplanets WASP-96 and HIP 65426b. Detailed imaging of HIP 65426b showed things that were previously unknown about this planet found in 2017. Its size, temperature, and approximate composition of the atmosphere. As for WASP-96, the telescope recorded the first clear evidence of the presence of carbon dioxide in the atmosphere of a planet outside the solar system. Further observations surprised scientists even more. Distinct traces of water were found, as well as evidence of clouds and haze in the atmosphere surrounding a hot gas giant planet orbiting a distant sun-like star. Right now, thousands of earthly telescopes and eyes of those craving knowledge about space are peering into the depths of space, as well as two brand new space telescopes, TESS and Webb. Although the science that studies exoplanets is relatively young, we're already seeing how man-made tools are pushing the boundaries of visible space further and further. Perhaps our new house can already be seen through their lenses.
Far away from Earth, Saturn is orbited by the most complex and mysterious satellite in the solar system. But what makes Titan such a unique celestial body in our solar system? Why did it draw so much attention to itself? The amount of incredible features on this satellite deserves its own documentary. Our video today will touch upon Titan's unique atmosphere, liquid present at the surface, a very Earth-like landscape, an ocean of warm water, rains that would take your breath away, and finally, a life form that not everyone will be able to imagine. These mysteries compelled us to research the information available about Titan and try to fit it all into one video. This satellite, which resembles the young, cold Earth from the past from the scientific point of view, invites you to take a deep dive into its mysterious nature. Among 63 known moons of Saturn, Titan immediately stands out as the largest one. And it's truly gigantic. Its diameter is 3,200 miles. It's larger than Mercury and only a fraction smaller than Mars. Although its size allows any amateur astronomer to study Titan even without a professional-grade telescope, until recently it remained a major mystery. This moon was discovered in 1655 by astronomer Christian Huygens, who noticed an object moving alongside Saturn. It had been spotted before but was assumed to be a star. It was first visited by the Pioneer 11 probe and subsequently revisited by Voyager 1 and 2. However, these first images could tell very little about the satellite, but they already showcase something unusual. The haze that obscured Titan from the eyes of the scientist turned out to be layered, its top layer mainly composed of hydrogen and nitrogen. Further attempts to study Titan using the Hubble telescope weren't successful. The research was revived by renowned astrophysicist and promoter of planetary science, Carl Sagan. He was the one to suggest that if the temperature on the surface of Titan is negative 290 Fahrenheit, then the methane that turns liquid at that temperature could be spread across the entire surface, which would mean that Titan is the place to go if you want to see an ocean of methane. Anyone who uses a gas stove is familiar with methane as the gas we light for cooking. Now imagine a place where this gas became a liquid, where it falls from the sky in the form of rain, fills methane rivers, and where these rivers flow into gigantic methane seas. In 1997, the Cassini probe was sent to Saturn with a mission to study the planet itself as well as its satellites. Even though Titan wasn't the main focus of this journey, the Cassini probe included a special lander spacecraft, Huygens, that was launched toward Titan in 2004. And almost half of the data recorded in the process of its landing was lost. We have the opportunity to experience the journey to the surface of Titan. The descent took about 2.5 hours. The atmosphere on Titan turned out to be so dense that Huygens floated down with a parachute veered from its course and was spinning so fast that many images taken throughout the process were ruined. The journey down to the surface also revealed the extent of the atmosphere. Turns out, it reaches over 300 miles above the surface, which is a record height for the entire solar system. The atmosphere of Titan is quite clearly separated into several layers, composed of different substances, and very diverse in terms of temperature. While the temperature on the surface is negative 290 Fahrenheit, at the height of 200 miles it's much warmer, only negative 130 Fahrenheit. At the very top, the Titan sky turns blue as it's filled primarily with nitrogen and hydrogen, but at the height of about 250 miles, the aforementioned orange haze begins to form, which continues all the way down to 60 miles, only clearing as you approach the surface. At the height of about 30 miles, the surface of the satellite becomes visible. To many people, it will look quite familiar as the landscape includes mountains and rivers. During the landing of the Huygens, it was discovered the orange haze layer is fairly evenly opaque all the way through. Here, the sunlight never really reaches the surface. This is what a sunny day on Titan looks like at noon. While the surface has texture, it's still relatively flat, with the highest parts of the land only rising as high as 0.6 miles. Take a look at this first image taken by Huygens upon landing. It's likely that the spacecraft landed in a dried-up bed of a methane river, leaving behind some smooth ice rocks that look like pebbles. They will have been preserved since the time the river was still full of liquid methane. That was pretty strange. There were no traces of liquid, Where did the supposed methane rivers go? After the images from the landing were processed, a few of them were combined into this collage. Here you can see an image of a river system with many streams branching off, not too dissimilar to some of the places on Earth. This prompted several theories as to where the liquid could have disappeared. The first theory sounds pretty earthly. As Titan undergoes the changes of the climate cycle, these rivers are filled with methane rain, and afterwards they dry up again. The second theory put forward by the scientists was that these methane rivers drew liquid methane from underground springs, which no longer function for some reason. Next, the Cassini probe will collect more data over the course of 127 flyby missions in Titan's orbit. For starters, thanks to this photo of the atmosphere taken by Cassini, we could begin to decipher the reasons why Titan's atmosphere is so opaque. Thing is, it's made up of multiple layers. The first layer is basically the biggest factory, producing complex organic compounds in the solar system. Right there at the height of over 300 miles, methane, nitrogen, and hydrogen are exposed to sunlight and transformed into more complex elements, which then begin to descend towards the surface, creating a new layer. The second layer is situated between 200 and 250 miles away from the surface and is made up of a tholin haze. An example of tholins on Earth is soot produced as a result of a combustion process. The third layer starts at around 200 miles. It consists of the inert gas ethane. Here, scientists noted a unique anti-greenhouse effect. On Earth, gases in the atmosphere trap heat and warm up our surface, resulting in the greenhouse effect. On Titan, tholin haze and ethane create the opposite effect, essentially forming a shield and maintaining both the heat from the sun at an altitude of 250 miles and the cold temperatures of negative 290 Fahrenheit degrees near the surface. At the height of approximately 60 miles, Titan even has some clouds, though very few. And although the climate on Titan changes very quickly compared to Earth, very recently there was a real tropical methane storm recorded around the equator of this moon. Take a look at the way it looked from Cassini. Thanks to its unusual shape, this storm was nicknamed the Arrow. It spread across an area of 200,000 square miles. The methane rain that was falling from the sky during the storm looked very unique compared to the rains we have on Earth. Imagine raindrops the size of a pear descending so slowly you could easily dodge them. Huygens and Cassini were able to confirm the composition of the atmosphere. Similar to Earth, the atmosphere on Titan is mostly nitrogen. However, it also contains 3.5% methane. But that wasn't the interesting part. On Earth and many other planets, the chemical processes take place near the surface. On Titan, however, its chemical reactor is located at the altitude of 300 miles, which results in huge amounts of organic compounds descending to the surface. Over 4.5 billion years ago, Earth was exactly the same. The only difference being that Earth was warmer due to its proximity to the sun both then and now, and the organic substances that fell from the sky did not fall into the methane soot surface and liquid methane, but into the oceans full of water. After studying the composition of the atmosphere and its layers, scientists came face to face with yet another mystery. It's been calculated that the methane that is now in the atmosphere should have disappeared 10 million years after the formation of this atmosphere, and yet it did not. Something continues to fill the atmosphere with methane, maintaining its level for more than 4.5 billion years. Some scientists have suggested that in the process of Titan's formation, there was so much methane that the supply has not dried up to this day. Others have suggested that methane is produced by some type of chemical processes taking place on the surface, and even that there are organisms that produce methane as part of their life cycle. This was the first hint of potential, albeit primitive, life on Titan. The second mystery for the scientists was the amount of hydrogen in the atmosphere. There's supposed to be 2.5 times less. It wasn't clear where so much of it comes from and why it's so unevenly distributed. At the surface level, there is less hydrogen than there should be, in contrast to the hydrogen content closer to the top, of which there is twice as much as there should be. This led the scientists to think about biological processes that may be using hydrogen that descends to the surface, creating a shortage. Leaving these questions unanswered, let's turn our attention to the surface of the moon for a while. First, take a look at this photo taken using the VIMS camera. This is an approximation of what the surface would look like. This is an approximation of what the surface would look like to the human eye. Looks a lot like Earth, doesn't it? The following images make that resemblance even more pronounced. This topographic map, captured using a radar, once again creates a sense of déjà vu when we compare it to Earth. It should be noted that there are very few craters created by meteorite impacts on Titan. The largest of those, the Minerva crater, spans 500 miles in diameter. The absence of craters can be explained by the extremely dense atmosphere, where anything small simply burns out. However, in these circumstances, these are still too few. This poses a problem for scientists researching the surface. It significantly reduces the chances of figuring out the age of the relief. As a result, scientists cannot say for certain how geologically active Titan is and whether it has a system of tectonic plates like Earth. In fact, its surface is suspiciously smooth. Let's take a look at Titan without the atmosphere to pinpoint our next point of interest. Initially, the dark areas that you see aroused a lot of interest in scientific circles. The scientists theorized that that's where the methane oceans were located. However, when Huygens landed in that exact area, it didn't find any liquid. Upon closer examination, it turns out these dark spots are deserts. When they were compared against Earth deserts, it became clear they are extremely similar and formed as a result of the same processes as on Earth. Due to the climate system operating on Titan, with its own seasons and wind patterns, a dune system composed of tholin soot and organic substances was formed. Except on Titan, due to low gravity, a wind of 11 miles per hour is enough to start a dust storm. Although the sand on Titan is organic, unlike on Earth, the scientists are still searching for an answer as to what created it. Initially, it was assumed that this sand was created from the remnants of methane that falls from the sky when it rains, and since in its liquid form methane takes tholin soot from the atmosphere down to the surface, as the methane dries up, the particles left behind form this sand. But it rarely rains on Titan. So now the leading theory is that this sand simply falls out of the tholin haze directly onto the surface, kind of like snow covering the surface of the satellite. After studying the first pictures that showed the beds of dried up rivers, the scientists set about searching for the liquid, and the first methane lake, Ontario, was found at the south pole of Titan. It is the only remaining lake in that area. However, many dried up lakes have been found nearby. Scientists are still arguing what may be at the bottom of these lakes and what their shores are made of. Whereas at the North Pole, entire seas were soon discovered with rivers flowing into them. And although the Kraken Mare and the Ligeia Mare are unique objects in their own right within the solar system, as this is the only place where liquid has been found on the surface except for Earth. The main mystery is still the answer to the question of whether this satellite can sustain life. There are two approaches to consider. Based on the conditions we are accustomed to on Earth, we should pay attention to the following fact. Cryovolcanoes have been discovered on the surface of Titan, where liquid water bursts from the cracks in the surface, which means that under Titan's icy surface is an ocean of warm water. It does not come into contact with the core of the satellite and is sandwiched between two layers of ice crust above and below. However, thanks to the attraction from Saturn, It's obvious that ebbs and flows occur in it, which not only heat this ocean but also split the upper shell of ice. Water mixed with large amounts of acetone breaks out to the surface, and there it mixes with the same organic sand that falls from the sky. Together, this creates the same conditions on the surface of Titan that were on Earth 4.5 billion years ago. The only difference is that Titan is much further away from the sun and significantly colder. That's why these processes are so fascinating to scientists. After all, they may lead us to understand in what conditions life appeared on Earth. We could call the other theory life according to Titan. It would seem that in such a cold environment and with such a huge amount of hydrocarbons without oxygen and water present, there's no life, and there could not possibly be. Indeed, the surface is basically a frozen gasoline lake. However, life is still possible, even in these conditions. Scientist Chris Mackin suggested that on Titan, the existence of methanogen bacteria is possible, just as it is on Earth. These bacteria feed on hydrogen and acetylene and live in this substance, producing methane as a result of that activity. This explains why there's so little hydrogen near the surface and why there's so much methane in the atmosphere, even though it should have evaporated a long time ago. It would seem that this could be the answer. And yet, a small problem remains. Methane and ethane do not act in the same way as water in regards to development of life. Water is an excellent solvent, which helps microorganisms get rid of waste and dissolve toxic substances. Methane and ethane in liquid and solid form are not suitable for work with the cell membrane, the part of the cell that performs the functions of filtration and protection. But more recently, Chinese scientists have managed to synthesize ozotosomes. These are organic compounds that could make up a protective membrane for a cell that lives in such an environment. And it's possible for this type of membrane to occur in methane and ethane on the surface of Titan. Additionally, observation through ALMA telescopes in the Mexican desert revealed that there is a substance from which the ozotosomes that would protect a living cell on Titan can be created, and in such quantities that could host up to a quintillion of such organisms within 10 square feet. Any other attempts to deny the possibility of life in a methane environment were shut down by the discovery of an unusual asphalt lake on Earth. It's composed almost entirely of natural asphalt, petroleum, and many complex hydrocarbon compounds. Samples taken from it showed millions of live anaerobic bacteria. Granted, these bacteria were incredibly ancient, but living perfectly fine in such an environment on Earth. Moreover, these bacteria feed on hydrocarbons and break down crude oil. Although the temperature regime on Titan is much lower than Earth's, and the chemical processes are slow and atypical for our planet, life on the satellite is possible and may even be pretty diverse, not dissimilar to life that originated on Earth 4.5 billion years ago. The kind of life we can even imagine. After all, it can exist both on the surface and under the ice in a warm ocean of water. All that we and scientists can do is wait for the next trip to Titan in order to get closer to unraveling the mystery of how life is born. But even now, you, just like thousands of other enthusiasts, can look through telescopes with keen interest studying Titan, a cold but living mirror of the Earth's past. Having lost its planet status, it would seem that Pluto was no longer on the scientists' minds. Now just a lifeless, frozen piece of space rock on the edge of our system. But over the last 7 years, just like the icy moons of Jupiter, Pluto proved that it is worthy of attention in the status of an object of interest. The most unique volcano in the entire solar system, snow that burns, an ocean full of water, a source of heat within the planet, cosmic smog in the atmosphere, ice mountains, and a bubbling nitrogen glacier. This is just a fraction of incredible discoveries on Pluto.
Because as it turns out, there's a possibility of life on Pluto. Although it was discovered relatively long ago in 1930, it remained a mystery for a very long time. Even then, it was clear that this planet, due to its remote location and small size, will require face-to-face time. Take a look at the best picture of Pluto, taken by the Hubble Space Telescope in 2006. This was the best we could do, and yet it's difficult to see anything concrete in this collection of pixels. Not long ago, the meeting with Pluto finally happened. But first, let's examine what we already know about Pluto before this visit. Let's bring our attention to the fact that Pluto has 5 satellites. The closest and biggest one, Charon, does not actually orbit Pluto, but instead they move together. Pluto and Charon are even sometimes referred to as a double planet. They orbit the center of gravity between them. This is the only pair of objects in the solar system that interacts in this manner. This is what that looks like. As we take a closer look at the movements of another satellite, Nix, it turns out that the other moons of Pluto move in a pretty chaotic way, which is also unique for the solar system. The New Horizons mission, which commenced in 2006, planned to visit Pluto and take the first proper photographs of it right from its orbit. It appears that Pluto was not in the mood for guests, and at the most crucial moment, the connection with the probe was lost. Thankfully, there's nothing mystical here. The probe systems simply weren't able to withstand the number of commands received from Earth in regards to the maneuvering and photographing the planet, so they shut down and switched control over to the reserve computer. You can only envy the enthusiasm and perseverance of scientists, and after 3 sleepless nights trying to reboot the probe before it approaches Pluto, it was a success. The probe began to orbit Pluto, and soon we received these images. In these images, we're able to see ice mountains, some reaching 2.5 miles. There was also a large number of craters, which is normal since every object in space is subject to being bombarded by asteroids. Did you spot the most unusual thing about these photos? This white area at the center of the planet immediately caught the attention of scientists. It was nicknamed the heart of Pluto, and this heart has an actual beat. It's believed this zone appeared at the site of a relatively recent, by space standards, collision of the planet with an object about 125 miles in diameter a few dozen million years ago. However, there's something unique about this birthmark on Pluto's face. Take a closer look at these pictures. As you may have already noticed, almost the entire surface around this area is riddled with various craters. Some of them are larger than others, but they are all pretty old. And yet you won't spot any craters on the white heart of Pluto. This could only mean one thing. This area and its surface is a result of a geological activity during which the crater that formed upon impact was filled with this white substance. Pluto essentially healed its wound. Pretty quickly, the scientists were able to use a spectrometer to determine it was nitrogen, which is the same substance the snow and mountains photographed by the probe are made of. However, this begs the question, how is it possible that a planet with an average surface temperature of negative 400 degrees Fahrenheit has nitrogen that could take liquid form and fill the aforementioned crater? This alerted the scientists to the fact that Pluto has a high-temperature core, and it's even possible that underneath the icy surface, there's an ocean full of water. After closely studying the patterns on the nitrogen ice, the scientists were able to discern something else. The nitrogen ice at the heart of Pluto is bubbling.
Not quite the same way of what you see in your kettle, but over thousands of years, something underneath the surface makes the ice bubble and crack. Studying these patterns made it clear. They were caused by the process known as convection. You can observe this process by watching the way clouds form in the Earth's atmosphere. Similar processes take place on the surface of the Sun. Like a fingerprint, convection marks the movement of heat within various substances. And the bubbling ice on Pluto is yet another proof of the heat bursting out from underneath its surface. The next mystery for scientists to uncover was this spot. It looks remarkably like an Earth's volcano, and the texture of the surrounding area resembles the aftermath of volcanic activity. But how would volcanoes form on Pluto? Upon closer examination of these images, it emerged that the substances erupting from this volcano was water. But with the surface temperature as low as this, how is it possible for the water to flow? The answer turned out to be pretty simple. Knowing high school chemistry was enough for the scientists to solve this mystery. If you mix water with ammonia, its freezing temperature is significantly lower. Take a look. In the temperatures close to the surface temperature on Pluto, water mixed with ammonia turns into a thick paste and can flow in a similar manner to lava. It's evident that the temperatures underneath the plant's surface are significantly higher than the scientists can imagine. But where could this heat be coming from? We're used to thinking that our planet is heated by the sun, and this temperature, along with the influence of the solar radiation, is the reason our planet retains a huge amount of heat. But that's not the case. Our planet, just like any other geologically active planet in the universe, contains a huge amount of heat under the surface. Although the sun heats our planet to a certain degree, it primarily heats the surface. This heat doesn't penetrate much deeper, even though the solar radiation does reach the inside of our planet. It's precisely the presence of a large amount of radioactive and heavy elements at the core of the planet that causes the geological activity and creates the heat within the planet. The scientists assumed Pluto would be different. For starters, it's very far away from the Sun. Before it was demoted, it was considered the furthest planet of the solar system. The size and density of Pluto also did not indicate the presence of radioactive or heavy elements that could accumulate this amount of heat. The last issue when it came to understanding the temperature on Pluto was the fact that its modest size prevents it from retaining heat. But Pluto proved everyone wrong. So how is it possible for the heat to remain on Pluto? The substance covering the surface of the planet turned out to be more than just ice and snow. It looks like ordinary snow. It's as cold as ordinary snow. But if it were exposed to fire, it would burst into flames. What makes the snow so special? At the temperatures of -375 to 400 degrees Fahrenheit, the water crystals trap a large amount of methane molecules. Like a blanket, this substance shields the warm radiative part of the planet from the cold surface and influence of the cosmos. This is how Pluto is able to retain heat. Let's move away from the surface for a minute and take a look at this image. The blue haze that you see is Pluto's atmosphere, full of nitrogen. Sure, its atmosphere is not exactly appropriate for habitation because it's mainly composed of nitrogen, has a fairly thin consistency, it doesn't retain heat, and we wouldn't be able to breathe here. Studying the atmosphere, which stretches to 125 miles above the surface, the scientists noted that it has a precise structure and is filled with something resembling smoke. This haze prompted intense arguments, but further research determined that it is smog. But why would there be smog on Pluto?
Turns out there's something else in the atmosphere aside from nitrogen: carbon monoxide and methane. We're used to the fact that on our planet, smog appears in connection with some form of a burning process, and some of it happens as a result of human activity. But Pluto has no cars and no breathing, living life forms. Or does it? Continuing their research, the scientists tried to recreate the composition of Pluto's atmosphere here on Earth to understand what causes the smog. By comparing the causes of smog on Earth and conditions on Pluto, scientists quickly came to the conclusion that this smog is caused by the way the sun's rays affect the gases in the atmosphere. They make the gas molecules break down, transforming them into soot, which subsequently turns into the haze of smog as it spreads through the atmosphere. Under the influence of gravity, this soot falls to the surface, turning into rain and giving the planet its signature brown-red hue. The more sunlight the surface is exposed to, the more red it appears. But the most amazing discovery was the nature of the aforementioned soot. Let's briefly come back to Earth and rewind time to 400 million years ago. Back then, our planet was a water world, with never-ending rain and thunderstorms raging above the surface. The composition of its atmosphere at the time was similar to present-day Pluto. At that moment, the sunlight triggered the same processes as it currently causes on Pluto. In the atmosphere of ancient Earth, breaking down from gas molecules and forming into new, more complex elements were what we now refer to as the organic basis of life, nucleobasis. The particles that will go on to form the first chains of nucleic acid and subsequently DNA and live cells, the basis of life. And right now, these elements are falling from Pluto's atmosphere onto its surface in the form of rain. What's more, these elements get into the cracks, and in the process of cryovolcanism, they make their way under the surface, the place that, as we already know, has plenty of heat. Does that mean that this is enough for a life form, however primitive, to emerge underneath Pluto's surface? It's very possible, because the icy blanket is hiding an ocean. Upon studying the breaks and craters on the surface of Pluto, it became clear the organic matter does not only make its way under the icy surface, it also rises to the top of it. Take a look at this photo. The red streaks, stretching from the places where water mixed with ammonia erupted to the surface, tells us that plenty of organic matter already formed underneath the surface. No one has even considered that life on Pluto is a possibility. However, we can already see that this planet is not only geologically active and alive, it has enough heat and is able to retain it. Under the influence of the sun, a sufficient amount of organic basis for life is formed in its atmosphere. Evidently, there are areas underneath the surface warm enough to contain water in its liquid form. Water mixed with ammonia that burst out from the depths of the planet through the volcanoes we've seen earlier suggests that such areas under the surface are fairly ample. All of this is making scientists examine each new picture of Pluto with keen interest. And after the icy moons of Jupiter, it was Pluto that became the new focus of their interest in search of extraterrestrial life. Having sufficient potential for life to form, Pluto managed to prove that even having lost its status as a full-fledged planet and being demoted to a dwarf planet, it is still very much alive. The possibility of colonization of other planets is a matter that has been on people's minds for many years. In the future, once we can travel through space, we will move forward from one world to the next, inhabiting them with new life along the way and changing these new planets to resemble Earth.
Imagine hundreds or even thousands of planets colonized by humans. Life would bloom along the trajectory of our journey through space, and eventually, the galaxy will be filled with beautiful Earths. But how can we achieve a result like that? Just like in any major project, you have to start small. Could you imagine that in the next decade, humanity might start the colonization of our solar system? Today, we're heading to a neighboring planet to find out if life on Mars is possible. At first glance, the red planet, located only 7 months away from Earth, is completely unsuitable for habitation. Mars. On this planet, there are no rivers, no fresh air, no food. The force of gravity on the surface is twice smaller than Earth's, which would have an adverse effect on human health over time. The atmosphere there contains many gases toxic to humans, so an oxygen mask would be a must. A person would not be able to move around the surface without a spacesuit due to the low atmospheric pressure and constant solar radiation. So how would the first people on Mars and the subsequent colonists survive in such harsh conditions? First, let's tackle the matter of oxygen. Scientists have already made significant progress in that direction. In April of 2021, Mars rover Perseverance managed to extract oxygen from the atmosphere using a tool called MOXIE via a process known as solid oxide electrolysis. In theory, MOXIE can perform the same function as trees on Earth in the near future. Since this kind of technology already exists, it's just a matter of scaling it up to meet the needs of the future colony. As for water, the vessel that brings the first colonists is expected to be equipped with an efficient system of recycling water, similar to the one on the International Space Station. This creates a little bit of freedom for the astronauts while they search the planet for potential sources of water. We know that in the early stages of development of the solar system, there was water on Mars. Previous expeditions have already found water as part of the mineral and soil composition. Currently, discovered and reliably confirmed volumes of water on Mars are concentrated mainly in the near-surface layer of permafrost, dozens, nay hundreds of feet thick. The majority of this ice is beneath the planet's surface since it cannot stay stable in current climate conditions and quickly evaporates once on the surface. The only places cold enough for this ice to remain all year round are the poles, where the ice forms so-called polar caps. In those areas, the overall volume of ice is estimated to be 1.2 million cubic miles. For reference, the sum total of freshwater lakes and rivers on Earth only reaches 24,000 cubic miles. If the ice were to melt, it could cover the entire surface of Mars with a 115-foot layer of water. In 2018, after probing of the planet, the Marsis spacecraft discovered the presence of a subglacial lake on Mars 1 mile deep under the ice of the South Polar Cap, about 10 miles in diameter. This became the first known permanent body of water on Mars. And in 2021, the ESA satellite ExoMars, capable of peeking into the depth of several dozen feet, discovered large deposits of water in the so-called Mars Grand Canyon. Currently, this is by far the most accessible water source on Mars, making the Valles Marineris Canyon network a good place for our first colony on the red planet. The supplies from a spaceship won't last forever, so the colony will have to make headway in growing edible crops. Scientists are very optimistic about this process because of the composition of the upper crust of the planet. Martian soil contains many of the nutrients that plants need to grow and survive, such as nitrogen, potassium, and phosphorus. Once we have a stable supply of air, water, and food, we will have built an excellent platform for building a colony from available materials. Martian soil can serve as a good material for building shelter necessary to protect the settlers from solar radiation and dust storms. Of course, the technology most convenient to us would be construction with the use of mega 3D printers. This technique is already being used here on Earth, and it can prove itself quite useful in such harsh and limited conditions as on Mars. Of course, all the necessary provisions and equipment to create favorable living conditions for the first colony will initially have to be delivered by interplanetary spacecraft. But how do we get to this planet? Several projects to create suitable vessels are being developed as we speak, and the SpaceX Starship is currently leading in terms of progress. As of early December of this year, Starship will be launched on its first orbital test flight. The launch vehicle will be super heavy. A notable feature of this rocket is that the rocket itself and the ship are both reusable and can be refueled in Earth's orbit. Once the ship reaches its destination, it can be refueled using the natural resources present on Mars to refuel: water and carbon dioxide, which is very convenient for us. These factors greatly reduce the cost of production and the cost of transporting goods respectively. The colony will also need a source of electricity to exist. Everything, even the basic things like the extraction of air, water, and food, will need electricity to function. Fortunately, Mars has huge reserves of deuterium. Deuterium, also known as heavy hydrogen, serves as a fuel for thermonuclear reactions. Imagine 0.034 fluid ounces of liquid fuel from heavy hydrogen can produce as much energy as 20 tons of coal. All we need to allow us to develop a colony are fusion reactors. Speaking of those reactors, quite recently U.S. scientists have made a breakthrough in the field of thermonuclear energy. Scientists managed to obtain useful energy in a thermonuclear reaction. But the question remains, can this colony be self-sufficient? There will come a time when Mars will not need Earth to sustain itself, much like the United States found itself long before the Revolutionary War. Does that mean that life itself will be self-sufficient? No. While we will be able to grow our own food on the planet in greenhouses, what about wild animals, birds, fish, rivers, oceans? Thus, in many ways, terraforming becomes a necessity. Terraforming is essentially the process of creating another Earth. The general consensus is that terraforming is required for global colonization, and global colonization is required for terraforming. These concepts go hand in hand. So let's break down the terraforming process into stages that could bring life on Mars much closer to terrestrial life. At stage 0, we as colonists that arrive here first can only live in spacesuits with a sufficient supply of oxygen. At this stage, we're faced with problems such as low temperatures down to negative 193 degrees Fahrenheit, an atmosphere full of toxic gases, very low atmospheric pressure, which compares to less than 1% of the Earth's atmospheric pressure, and of course the cosmic rays penetrating everything on the surface of Mars. The thing is, Mars has little to no magnetic field, which could protect us from radiation. For reference, a person's exposure to radiation on Earth is 40 times lower. For the next stage, we'll try to get closer to creating conditions where it would be possible to leave the shelter with just the oxygen mask, without the need for a spacesuit. To do this, we need to take care of the radiation, temperature, and density of the atmosphere. Reducing the reflectivity of the Martian surface would allow for a more efficient use of sunlight in terms of heat absorption, which would warm up the planet's atmosphere. This can be achieved by spreading dark-colored dust from Mars' moons Phobos and Deimos, which are among the darkest celestial bodies in the solar system. The alternative is to introduce dark, extremophile microbial life forms such as lichens, algae, and bacteria. This way, the surface would absorb more sunlight, raising the temperature in the atmosphere. If algae or another type of flora took root, it would also introduce a small amount of oxygen into the atmosphere, although not enough for humans to breathe without assistance. In April 2012, scientists reported that the lichen survived and showed remarkable results regarding the adaptive capacity of photosynthetic activity during the 34 days of simulation under Martian conditions at the Mars Simulation Lab. That being said, Mars is already the second darkest planet in the solar system, absorbing over 70% of the incoming sunlight, so there's little scope for further dimming. Another problem with this method is the regular Martian dust storms. They span across the entire planet for several weeks at a time and not only increase reflectivity but also block sunlight from reaching the surface. Once the dust settles, it sticks to whatever it touches, effectively obscuring anything previously deposited on the surface from the sun's reach. The terraforming of Mars would entail three major changes, interconnected with each other: the creation of a magnetosphere, the creation of an atmosphere, and an increase in temperature. The atmosphere of Mars is relatively thin and has a very low surface pressure. Because its atmosphere is made up mostly of carbon dioxide, when Mars starts to warm up, CO2 can be helpful in keeping the thermal energy near the surface. Moreover, as it warms up, more CO2 from frozen reserves at the planetary poles should be released into the atmosphere, increasing the greenhouse effect. Another way to improve the atmosphere and subsequently create the greenhouse effect is the introduction of ammonia, methane, and other hydrocarbons. Large deposits of ammonia and hydrocarbons have been found frozen on small celestial bodies such as Titan, which orbit the solar system. It may be possible to redirect the orbital movement of these or similar small objects containing large quantities of the aforementioned substances so they collide with Mars, thereby releasing them into the Martian atmosphere. However, even if we can find a way to prevent its release into space, methane can only exist in the Martian atmosphere for a limited time before it's destroyed. Presumably, this gas will eventually be depleted via the same processes that strip Mars of much of its original atmosphere. But these processes are believed to have taken hundreds of millions of years. Still, well-known compounds that we've been generating on our planet for many years can come to our aid. Particularly potent greenhouse gases such as sulfur hexafluoride, chlorofluorocarbons, or perfluorocarbons have been proposed as initial means of raising the temperature on Mars and maintaining long-term climate stability. These gases create a greenhouse effect thousands of times stronger than CO2. It has been estimated that approximately 0.3 microbars of these gases would need to be injected into the Martian atmosphere to melt the CO2-laden South Polar glaciers. This is equivalent to about 3 times the mass of CO2 gases generated on Earth from 1972 to 1992, when their production was prohibited by an international treaty. Maintaining the temperature will require the constant production of such compounds as they're destroyed under the influence of the sun. It's been calculated that the introduction of 170 kilotons of optimal greenhouse compounds annually would be sufficient to maintain the greenhouse effect given the terraformed atmosphere. However, even with all of these efforts, it would be difficult to preserve the atmosphere from erosion by the solar wind due to the lack of a protective global magnetic field. One of the key aspects of terraforming Mars is to preserve the atmosphere, both present and future, from being dispersed into space. Some scientists suggest that creating an artificial planet-wide magnetosphere could help solve this problem. According to Japanese scientists from the National Institute of Thermonuclear Sciences, this can be achieved with the use of modern technologies by building a system of cooled latitudinal superconducting rings, each carrying a sufficient amount of direct current. The same report argues that the system's economic impact can be minimized by using it as a planetary energy transmission and storage system at the same time. Also, during the Planetary Science Vision 2050 workshop at the end of February 2017, NASA scientist Jim Green proposed the concept of placing a magnetic dipole field between the planet and the Sun to protect it from high-energy solar particles. Imagine a huge magnet located at the Lagrange point L1 at about 320 radii of Mars, creating an artificial magnetosphere. The magnetic field should be comparable to Earth's. This can be achieved with a 1-2 Tesla magnet. Once built and placed in orbit, the shield could allow the planet to partially restore its atmosphere and prevent further evaporation. Let's talk about another monumental structure. Imagine a huge mirror the size of West Virginia made of thin aluminized film. Such mirrors could be placed in orbit around Mars to increase the total exposure it receives. This would direct more sunlight to the planet's surface and could significantly increase the surface temperature of Mars. A mirror with a radius of 77 miles could be positioned as a satellite, using its efficacy as a solar sail to orbit in a stationary position relative to Mars, located near the planetary poles in order to release the CO2 deposits from the ice cap and contribute to the overall warming via the greenhouse effect. At the moment, the main obstacle is the difficult process of launching large mirrors from Earth. And now, finally, thanks to all the aforementioned manipulations, we will reach the final stage, although the journey to that point is likely to take hundreds of years. By introducing plants, increasing the overall level of oxygen, and creating new biomes on the planet, we'll be able to move around freely and breathe deeply, completely eliminating the need for additional devices that support our life. So, what awaits us next? Long term, once production outgrows the consumption needs, these steps will serve as a good basis for the extraction of rare metal such as platinum, gold, silver, and others that are so abundant on Mars. Getting from Mars to Earth is much easier than the other way around. Even more promising is the proximity of the asteroid belt to Mars. Dactyl, a small asteroid moon found in the belt, is 0.8 miles in diameter and is believed to contain more iron than the human race has ever used. These asteroids could be mined relatively near Mars and brought back with little monetary expense. Companies such as TransAstra Corporation and KESE are already planning to mine asteroids. An outpost on Mars would only make things easier. We might see a triangular trade route, much like the one that existed in the 18th century between Britain, the West Indies, and North America. The economic potential is enormous. Each of these steps presents a big challenge, but it's only a matter of time before people set off to conquer Mars. And yet we can already wonder, what awaits us after the successful colonization of Mars? Will we start mass mining asteroids to build a new economic system? Will we travel further to conquer the next planet? Or maybe we build a huge space station to study neighboring systems. The answer remains the same. We just need to start small.
Are we alone in the universe? Those involved in the search for extraterrestrial life have been increasingly sharing the view that mankind is not ready for contact with the alien civilization. It becomes obvious the moment we put the dreams and imagination aside and delve into the scientific approach. Not only can the search for intelligent civilizations be fruitless, but it can also lead to opening the door that we are not ready to walk through. What mysteries actually hide behind the cosmic silence? And why do we put so much effort into coming in contact with extraterrestrial beings, knowing that we may never achieve this goal?
After spending years exploring the possibilities of coming into contact with extraterrestrial beings, scientists had come to surprising conclusions. Let's imagine that alien civilization is at the same level of technological advancement as us, and their spacecrafts fly at the same speeds as ours. Turns out intelligent life with this advancement level needs less than 1 billion years to spread across a galaxy of the same size as ours. Just look at how fast the galaxy would actually have been inhabited by any civilization of this caliber. But if that were the case, why are we not seeing this lively galaxy around us? To answer this question, we'll need to take a look at the Kardashev scale. The majority of modern scientists use this scale to measure the potential ability of living organisms to colonize the surrounding space and subsequently the possibility of contact with other life forms. This scale gives its own answer as to why we are not seeing this image of populated space all around us. Kardashev proposed to measure a civilization's level of technological advancement based on how efficiently it uses their energy resources. According to this scale, a Type 1 civilization can learn to utilize all of the energy that they're able to harvest on their home planet, radiating from its parent star. This type of civilization is most likely ready for interplanetary travel and at some point down the line will be able to colonize its entire system. For context, we only use 73% of the planet's energy potential, whereas the amount of energy we learn to harness from the sun is less than 0.1%. Turns out we're still on level 0, according to this scale. Civilizations that have reached the status of Type 2 are capable of capturing the energy not only on their home planet, but also any energy they could harness within their star system. Or at the very least, they're close to being able to do that. In their search for this type of civilization, scientists are on the lookout for a Dyson sphere, a hypothetical artificial structure that would allow the civilization to harness all of the star's energy from within the system. These civilizations would be capable of interstellar travel. They will have actively colonized their own galaxy and possibly moved on to colonizing the surrounding areas, which would allow them to keep increasing the amount of energy that they could use. As well as using all of the energy of their star system, Type 3 civilizations are able to harness the energy from neighboring systems, control the energy of their entire galaxy, or even the entire universe. These civilizations are able to not only control this energy, but possibly change entire worlds. There's a simple reason as to why communicating with the Type 1 civilization is problematic. Upon calculating the capacity at which we can transmit and receive signals in space, we come to find that the maximum visibility of the Earth's energy activity, radio signals, lasers, electric activity, is very limited. We can only be seen or heard from a distance of 4 light years. The noise we create could only be heard by our closest neighbors who have reached the same level of development. Type 2 civilization would be able to hear us from much further away. They would also be able to ensure they remain unnoticed, either because of the great distance or because they wish to keep it that way. After 60 years of transmitting various signals and scanning the skies trying to detect artificial signals, we haven't been able to find anything and we remain unheard. The paradox of great silence was first raised by legendary physicist Enrico Fermi. Speaking to his colleagues once, he raised a seemingly simple question. Where are the aliens, and why have they not been to visit us? However, when you consider our civilization's level of development, the answer is pretty obvious. Why would they? The logistics required for interstellar travel are only available to civilizations that have reached Type 2 at least, and in their eyes, we're not worth it. What person in their right mind would try to communicate with ants? How would an ant be able to recognize that someone's trying to communicate with it? After all, in terms of our development and technological advancement,
Compared to them, we're akin to highly developed ants that have taken over an entire planet, not to mention the ineffective use of said planet's potential. Other civilizations that, like us, haven't yet reached Type 1, they stay confined to their own planet and star system. It's simply unrealistic to expect any guest from a place like that. It is possible that right at this moment they're working on the same problems as we are: starvation, fighting for resources, and pursuing minor and major wars for territories. And so it appears that Type 1 civilizations would simply have other things to worry about. However, is it possible that someone could have overcome those issues and decided to launch themselves into space? The data presented by the scientists suggests we may in fact have a surprisingly large number of neighbors. As we lift our gaze to the cloudless sky, we can imagine how many potential inhabited planets there are. What we see in the sky is only 1% of our own galaxy, the Milky Way. Even if only 1% of these worlds are inhabited and populated with conscious life, that would amount to around 100,000 intelligent civilizations that could exist in our galaxy alone. And they all remain silent. There are a vast number of solutions to the Fermi's paradox because there are around 100 scientific theories alone that attempt to explain this silence. Let's break down the most interesting of those theories. There are no signs of Type 2 or Type 3 civilizations because they don't exist. The scientific analysis tells us there are thousands of civilizations in our galaxy alone, hence they presume that there is a factor that stands in the way of their development. This factor is called the Great Filter. This theory suggests that after reaching a certain level of development, life faces an obstacle that's impossible to overcome. However, scientists don't know what this Great Filter may be. The possibilities are only limited by our imagination, from artificial intelligence, which cleanses the overly developed organic life from the galaxy, to various forms of apocalypse. The most unfortunate thing about this theory is that, if true, humanity is faced with three possible prospects in the future. According to the first scenario, we as humanity are a unique life form that has managed to overcome the big hurdle of the Great Filter. That would mean that reaching our level of progress is very challenging, and the chances of it happening are very low. In this case, the cosmic silence would be caused by the majority of civilizations failing to overcome the Great Filter. Hence, we simply have nobody to come in contact with. The second scenario suggests that we happen to be the first ones among our neighbors to advance to this level. This would be due to the fact that the conditions necessary for the existence of conscious life had only been established relatively recently, and we happen to be the pioneers of this progress. In this case, we simply found ourselves in the right place at the right time to have become one of the first ultra-intelligent civilizations. It also means we have plenty of time to advance to become a Type 2 and Type 3 civilization. That's the reason why there's no hope for contact. We are progressing faster than any other organic form of life since the Big Bang. The third scenario presented by scientists is more pessimistic. They reckon that if we were not the first ones to reach this level of advancement in this rare sequence of cosmic events, then the Great Filter is still ahead of us. They think that life evolves at regular intervals until it reaches a certain stage, which is where we stand now. Whatever or whoever it is, it presents a challenge that prevents life from evolving to a Type 1 civilization, and it's unlikely that we would be an exception to this rule. Those favoring the third hypothesis believe that the cosmic silence is great news for us. After all, the presence of complex life on Mars, Moon, or somewhere else means that the Great Filter is bound to be ahead of us. There's also an opposing viewpoint. According to it, Type 2 and Type 3 civilizations do exist, and we haven't come across them for a reason. This is based mainly upon the fact that we're very much limited in our search. After all, we are searching for the signals that are only 100 light years away from us, which represents a mere 0.1% of our galaxy. The most interesting theories resulting from this version sound like this. Galaxy has long been colonized, and to the colonizers themselves, we are located in a low-interest deserted area. The perfect example of a similar situation happened in Earth's history: colonization of North America. Native Americans residing in the remote parts of the continent only learned about the presence of their neighbors, super-developed Europeans, several decades after the latter arrived on the continent. It's also possible the activity is present around our system. We're simply too primitive to understand these signals, or we are focusing our efforts elsewhere. That would be like trying to communicate with people using the internet via Morse code. It is equally possible that our minds differ so greatly compared to other life forms that our attempts to establish contact come across as senseless noise. Another interesting hypothesis is the cosmic zoo theory, which states that we are actually surrounded by a densely populated galaxy. Within this world, Earth is something akin to a wildlife reserve, the kind you could watch, but you're not allowed to go on a safari ride or make contact with such a primitive life form. And still, every attempt to explain this paradox inevitably comes to a stop. We still know very little about space, and we have not yet evolved to the level necessary for resolving these problems. But that doesn't mean that our attempts to find intelligent life have stopped, and humanity is frozen in place, waiting for outside contact. There are currently at least 2 projects that have spent several decades trying to establish contact and search for extraterrestrial life. These are the projects SETI and METI. The work of these 2 projects is based on the Drake equation, a mathematical formula that suggests it's possible to accurately calculate the number and, more importantly, the potential location of inhabited worlds. The next step is to use this information to reach out. According to this equation, our galaxy hosts between 8 and 2,900 systems of intelligent life. As science evolved and our knowledge about our galaxy grew, the calculations became more precise. Realistically, there should be 36 other brother worlds coexisting with us in the Milky Way galaxy. The SETI project started in 1984, and at first it focused on scanning our immediate surroundings in search of artificial radio signals coming from our potential neighbors. However, no signals were found. Right now, the major hope is that the European Space Telescope Gaia will bring some results. It's able to transmit information about the exact location of all stars in our galaxy and give an accurate assessment of every star system's potential. That's why the SETI project was able to move on from a rough estimation of various star systems to a detailed analysis of each one, thanks to a technological advancement. And now, every signal sent out there is directed towards the systems with the highest likelihood of intelligent life. Will we get a response from any of them? The answer to this is both yes and no. Some of the systems we have already researched are so far away that any response from them would take over 3,600 years to reach Earth. And last but not least, the mission of METI is also very important. After all, they help by trying to capture any messages from space and send our greetings to distant stars. We know of at least 8 attempted communications, 2 of which are the famous gold records on the Voyager probes and similar ones on the Pioneers. The other 6 are messages contained in radio signals directed towards some stars. For example, to one of the nearest solar-type stars, Gliese 581. So far, there have been about 40 radio sessions in total. We're unlikely to hear a response to them, but it is possible that our descendants might. To sum up the results of our small study, we can say quite definitely that the silence of the universe is normal.
It's also possible that we have not yet sufficiently evolved to make contact with the intelligence around us, or even that the cosmos itself is not yet ready for this. Which one of these scenarios is the most likely? Are we a unique species, or has the entire space been colonized by super-developed civilizations for a long while? We are close to uncovering the answers to these questions. But are we ready for this contact?